In this video, we're going to talk about the key features of parent functions that we're going to discuss in Algebra 2. So let's get to know the function families that we're going to be studying this year. We're not going to spend a whole lot of time talking about linear and quadratic families because we already learned about those in Algebra 1. So we're going to learn about absolute value functions, square root functions, rational functions, cubic and cube root functions, and exponential and logarithmic functions. So before we study the details of each function family, let's learn about the important characteristics of the parent functions. And if you remember, in the previous video, we spent some time discussing these important characteristics. And they are the domain and range, intercepts, symmetries, asymptotes, and the minimum and maximum. So it's important to remember that every family of functions will not have every feature, but they will have at least some of these. So also it's a good idea to have the blank notes available today to follow along with me. I will also upload the chart that has all the information filled in for you, but if you open the blank notes for this lesson, you'll see that it has this chart and there's some information missing from this chart. So we'll fill that in as we work through this video. So here are some key features of the linear parent function. So this is already filled in for you because I know you're very familiar with the linear parent function from Algebra 1. The domain and range are all real numbers, and it also intersects the x and y axis at 0, 0. This graph has rotational symmetry about the origin. So what I can do is if I imagine this origin as a pivot point, okay, and then if I take this graph and I rotate it, notice that I can actually create the same exact graph. So that's why the linear parent function has rotational symmetry. So here's the quadratic parent function. This information is also already filled in for you because I know you learned about this in Algebra 1. So it has a domain of all real numbers, and the range starts at 0 because 0 is the lowest y value, and then it includes all y values up to positive infinity. So it intersects the x and y axes at 0, 0. 0, 0, we also find the vertex of this graph. That vertex will be a minimum because the y value of 0 will be the lowest y value on this graph. So it has a minimum of 0 at x equals 0. This graph also has reflectional symmetry with respect to the y-axis because if I take this graph and flip it over the y-axis, notice that I create the exact same graph. So now let's discuss the key features of the absolute value parent function. So the absolute value parent function is f of x equals the absolute value of x. So actually the absolute value parent function will be very similar to the quadratic parent function. Notice that it does include all values of x. So we're going to say that the domain goes from negative infinity to positive infinity. The range, well, the lowest y value is going to be here at 0. So the range is going to start off at 0, and then it goes up from there. So it's going to go up to positive infinity. So notice this graph intersects both the x and y axes at 0, 0. So it'll have an x-intercept and a y-intercept at 0, 0. This graph also has reflectional symmetry because if I take it and if I reflect it over the y-axis, notice that it is the exact same graph. So we're going to say it has reflectional symmetry, and that will be with respect to, you can say either the y-axis or you can write that as x equals 0. So it's also going to have a vertex. That vertex will be at 0, 0, and that's also going to create a minimum value. So it's going to have a minimum of 0 at x equals 0. Now let's discuss the key features of the square root parent function. So let's talk about all the possible x values. Well, notice that the lowest x value is here at 0. So the domain is going to start off at 0, and then it goes to the right to positive infinity. So it's going to be 0 and then positive infinity. And then for the range, well, the lowest y value is also at 0. So it's going to start off at 0, and then from there, the graph goes up. So it's going to go 0 to positive infinity. It does intersect both the x and y axes at 0, 0. So that's going to create both our x-intercept and y-intercept at 0, 0. This function has a minimum because notice that 0, 0 is the lowest point, and then from there, the graph goes up. So it has a minimum of 0 at x equals 0. Now let's discuss the key features of the rational parent function. So this is an interesting function because notice that the domain is not continuous. Like you see that here this graph continues and then there's kind of like a break in the function and then we have a second piece to our graph. So we're going to have to describe the domain in two pieces. It starts off at negative infinity, so we'll say it goes from negative infinity and then it goes to 0, but it doesn't actually include 0. Okay, what happens is it gets really, really, really close to x equals 0, but it doesn't include it. So we're going to say negative infinity to 0. And then remember, we have to describe the second piece. So to do that, we're going to use the union symbol, which means and basically, right? So we have negative infinity to 0, and the second piece starts off at 0, but doesn't include it. So we have 0, and then it heads off to the right. So we say it goes to positive infinity. So the range actually also does something similar because if we look at the y values, notice that they go up and then there's kind of like a break at y equals 0, and then it continues up from there. So we'll say that the range goes from negative infinity to 0 and 0 to positive infinity. So this rational parent function is very interesting because it has lots of different types of symmetry. So what happens is if I draw in the line like this, okay, the line will have the equation y equals negative x. And this graph actually has reflectional symmetry over that line. So we're going to say it has reflectional with respect to y equals negative x. Also, if I draw in the line like this, that is the line y equals x. The graph also has reflectional symmetry with respect to that line. So we'll say y equals negative x and y equals x. This graph does also have rotational symmetry. So if I take this and rotate it about the origin, okay, notice that I can actually create the exact same graph. Okay, so we'll say that it has rotational symmetry about 0, 0. Okay, so lots of different symmetries going on here. Another interesting feature of this graph is that it has some asymptotes. Asymptotes occur where there's some interesting behavior going on for our function. So it has a vertical asymptote anywhere an x value is not defined. So we just said that x equals 0 is not defined, so it's going to have a vertical asymptote at x equals 0. It has a horizontal asymptote at a place where the x values head off into infinity. So notice that around y equals 0, x heads off into infinity in both directions. So it's going to have a horizontal asymptote at y equals 0. So now let's describe the key features of the cubic parent function. So the cubic parent function, f of x equals x cubed, actually does include all x values in the domain. So we'll say the domain goes from negative infinity to positive infinity. The range also does include all y values, so the range is going to go from negative infinity to positive infinity. It does intersect both the x and y axes at 0, 0, so it has the x-intercept and y-intercept at 0, 0. So this graph does not have reflectional symmetry, but if we take it and rotate it about the origin, notice that it does have rotational symmetry. So we would say that it has rotational symmetry about 0, 0. Okay. All right, now let's try the cube root parent function. So it does include all x values in the domain, so we're going to say negative infinity to positive infinity. The range also does include all y values, so we're going to say it goes from negative infinity to positive infinity. It does intersect both the x and y axes at 0, 0, so we're going to say that's where our x-intercept and y-intercept are located. So it doesn't have reflectional symmetry, but if I take this graph and rotate it about the origin, notice that I do create the same function. So it has rotational symmetry about 0, 0. So now let's describe the key features of the exponential parent function. So exponential functions are really interesting because we don't have just one parent, we have several different parents. And that's because exponential parent functions have different bases. So the base is going to create a subfamily. So we're going to create a family within the exponential family that's called a subfamily, and then everything in the subfamily will have the same base. So for example, we'll have all the functions that have base 2. You'll notice that the other two parent functions have a base of e and a base of 10. So those are just some examples, okay? So I know the other two are filled in because all the parent functions have similar characteristics. So I'm just going to go over the features of the parent function that has a base of 2. So notice that the domain, it does include all x values. So we say that the domain goes from negative infinity to positive infinity. So notice what happens with the range. The y values get really, really close to 0, but they don't actually include 0. So we're going to say that the range goes from 0 and then it heads up into positive infinity. So now let's think about the x-intercept. The x-intercept occurs where y equals 0, right? Because the x-intercept has the form x0. Well, if 0 is not included for our y values, that means it can't have an x-intercept. So we're going to say this graph has no x-intercept, but now let's think about the y-intercept. You can see from this graph that does include a y-intercept. The y-intercept is going to be 0, 1. Because if I plug in x equals 0 to my function, I get 2 to the 0, which is equal to 1. This graph does have a horizontal asymptote. It has a horizontal asymptote at y equals 0 because you can see that's where the x values head off into infinity. It has no vertical asymptote because remember, a vertical asymptote will only exist where the function is not defined for a specific value of x. Now let's try describing the key features of the logarithmic parent function. Just like exponential functions, logarithmic functions have different subfamilies, okay? And those subfamilies are determined by the base of the logarithm. So the parents that we have in our chart are log base 2, log base 10, and log base e. So I'm just going to go over the log base 2 parent with you because all of these parent functions have very similar characteristics. So let's think about the domain. Notice that the domain does not include all real numbers because it does get really, really close to x equals 0, but it doesn't actually equal 0. So the domain is going to go from 0 to positive infinity, but the range does in fact include all real numbers. So we're going to say negative infinity to positive infinity. So now let's think about the x-intercept and the y-intercept. This graph does have an x-intercept, and we can see that the x-intercept is at 1, 0. What about the y-intercept? Well, remember the y-intercept occurs where x equals 0, right? Because it's 0, y. Well, we just said that 0 is not included in the domain. So that means that this graph does not have a y-intercept. Now let's think about a horizontal asymptote. There's no place where it's just heading off to infinity, so we're going to say there is no horizontal asymptote, but it does have a vertical asymptote, right? Because this function is not defined for x equals 0, so we'll say it has a vertical asymptote at x equals 0. So by studying the parent functions, we can begin to learn about the key features of families of functions. Remember to keep the chart that we created today to use as reference throughout this course.